We're now going to look at the binomial distribution. Binomial distribution. And the idea here is that there are certain situations where a random variable is going to have something called a binomial distribution. So it's a special type of random variable. And to show you when this happens, let me start out with an example of something that has a binomial distribution. And then I'll explain why this has a binomial distribution. So let's say there is a 3% chance of catching a disease. Okay, now let's say 50 people are exposed to the disease. Okay, and then we're going to let x equal number of people who catch the disease. Okay, now x will be a random variable that has a binomial distribution to it. And let me explain why that is. Okay, so first of all, there is a fixed number of identical trials. So there is a fixed number of identical trials. So in this situation, notice 50 people are exposed to the disease, and each person is like a trial. It's like you're going to take the person, expose them to the disease, and either they catch it or they don't. So let's say I have two receptacles over here. One is I put the people that catch it, the other one are the people that don't. Okay, then I take another person, expose them to the disease, and either they catch it or they don't. I take third person, expose them to the disease, either they catch it or they don't. Take a fourth person, expose them to the disease, they catch it or they don't. Fifth person, expose them to the disease, they catch it or they don't. Sixth person, expose them to the disease, catch it or they don't. And don't worry, I'm not going to go through all 50 people, but I wanted to do it enough to show you, the monotony here. You're doing the same thing over and over again, and what you're doing is exposing someone. So each person is a trial where they get exposed and either they catch it or they don't. Okay? So in this case, there's 50 people. So n is equal to the number of trials. So in this case, n is equal to 50. Okay, so these numbers that we get are going to be important because they are going to be the numbers that go into the binomial probability formula in a minute. Okay, so this is binomial, first of all, because there's a fixed number of trials. Second of all, it's binomial because each trial results in one of two complementary outcomes. Okay? So when I take someone, expose them, and they catch it or they don't, there's two possible outcomes. Either they catch the disease or they don't catch the disease. Okay? And those are complementary events. Okay? The probability of one of those is 1 minus the probability of the other one. Okay? Now what we're going to do is we're going to call one of those events a success, and the other event will be a failure. Okay, but the success isn't necessarily the positive of the two outcomes. The success here is what you're counting up here. So in this case, I'm counting the number of people who catch the disease. So the success here would be catching the disease, right? And then the failure would be not catching the disease. Okay? So P is going to be probability of the success. Q will be probability of the failure. Okay? And so you could these are complementary events. So P is 1 minus Q. Q is 1 minus P. So in the problem, they will give you either P or Q, and then you get the other one by taking 1 minus the one that they give you. So in this case, since I'm counting the number of people who catch the disease here, then the success the success is the probability of catching the disease, or the success is catching the disease, and P is the probability of that happening. So in this situation, the P is what they give you, 3%. So P is 0.03. Okay? Q then would be the failure, in this case not catching the disease, and that would be 1 minus 0.03, which is 0.97. Okay? So a situation, a random variable is binomial when there's a fixed number of identical trials, and n is equal to the number of trials. Okay, and each of these trials results in one of two complementary outcomes. Okay, a success and a failure. The success is what X is counting. Okay, the failure is the other outcome, and P and Q are the probabilities. Okay, and then the final thing here, number 3 here, the final thing is that the random variable X counts the number of successes out of the n trials. Okay, so it's going to be binomial. The random variable X is binomial if it's counting the number of successes out of the n trials. So you got identical trials, they result in one of two outcomes. In fact, that's why this is called binomial. Like a bicycle has two wheels, binomial has two trials here. And one's a success, one's a failure. And then if X counts the number of successes, then X has a binomial distribution. Okay? So now the thing is, we can find the probability. You can almost think of X here as having a binomial distribution, right? Where this would be 0, 1, 2, 3, 4, 5, on up to n. So you could have no successes, 1 success, 2 successes, 3 successes, 4 successes, 5, on up to n successes. And then each one of these has a probability, right? So this would be like probability X equals 0, probability X equals 1, probability X equals 2, so on, probability X equals n. Okay, and now the binomial probability formula is what you can use to calculate any of these probabilities. Okay, so we have n number of trials, we have the probability of a success, probability of a failure, and then we have an X up here. So like, let's say I wanted to find the probability of getting 2 successes. Well, the binomial probability formula would tell me what that probability is, and it would like go right here for 2 successes. Okay, so here's the binomial probability formula. So the probability that that you get X successes, and And I don't know how else to do this. I don't want to say x equals x because that's just confusing. So the probability of getting x successes is n choose x, the probability of a success raised to the x, the probability of a failure raised to the n minus x. It's going to look like that. So this is the combination function on your calculator, and this is the probability of a success. Then you're going to raise that to the number of successes. This is the probability of a failure raised to the number of failures. So x is the number of successes. So n minus x is going to be the number of failures, right? If I have 30 trials and I want 5 successes, then I want n minus 5, 25 failures. So probability of a success raised to the number of successes, probability of a failure raised to the number of failures. So here's an example. In the example above, where n equals 50, p equals 0.03, q equals 0.97, find the probability that 2 people catch the disease. Okay, so using this, so now I can write probability x equals 2, okay, because I want 2 successes. 2 people catch the disease. Okay, so then in here, we got to look back. Remember, 50 people were exposed, so my total people, 50, and then I want to choose 2 of those to be successes. Okay, and then my probability of a success, 0.03, raised to the second power, because this is the number of successes, right? And then 0.97 raised to the 50 minus 2, which is the number of failures, 48 power. So I don't put n minus 2 up here. I do if I want 2 successes, then I want 48 failures. If I want 3 successes, I want 47 failures. If I want 10 successes, then I want 40 failures, so on. So it's really, out of 50, choose 2 successes, the probability of a success raised to the number of successes, the probability of a failure raised to the number of failures. And now we can plug all of this in our calculator. And we're going to do it at once because these can get really large and these can get really small. If we put them together in our calculator at once, they're going to balance out and give us the probability. So that's one reason why I don't want you to do these by hand. Just do them in your calculator. So it'll look like this. Out of 50, choose 2 times the probability of a success raised to, 0.03 raised to the number of successes, 2. So then I'm going to multiply that by probability of a failure, 0.97, raised to the number of failures. And notice I put all that in at once, just like that. And I don't need any parentheses or anything, even though I have them here so that you know that those are exponents and not further digits. In here, I don't need parentheses. The order of operations is going to work, and so it'll do the exponents and then do the combination, and then it'll multiply it all together and hit equals, and there it is, 0.2555 if I round to 4 decimal places. 0.2555. And that would be the probability that 2 people catch the disease. That 2 people catch. So this literally is what would go right here in my table, 2555. Okay? So, and all of these are going to add up to 1, right? So this gets a pretty big chunk that 2 people catch the disease. But that kind of makes sense because there's only a 3% chance of someone catching the disease. So to have like all 50 of them catch it would be astronomically small. Okay? But having 2 people catch it, that's about right. 2, 3, 4 people. That's about how many you would expect to catch it. So a lot of the probability is going to go down here. Okay? But this is the binomial probability formula. So let's do another problem so you can see how to get N, P, and Q and actually find the probability. And this is kind of how it'll look like in the homework. So let's say the or let me do this differently. Let's say 80% of adult males are shorter than 6 feet. Let's say. I don't know if that's true. I'm making it up. But let's say that's true. In a certain population, 80% of adult males are shorter than 6 feet. And then let's say a sample of, we'll say, 35 adult males is selected. And let me do something real quick. So, what is the probability that exactly 7 people are 6 feet or taller? Okay, so here's a nice problem. 80% of adult males are shorter than 6 feet. A sample of 35 adult males is selected, and we want to know what the probability that from that sample exactly 7 of the people are 6 feet or taller. Okay? Now, first of all, the success is what I want to find the probability of. So in this case, the success is being 6 feet or taller. That is the success. But notice the percentage I'm given here, 80% of adult males are shorter than 6 feet. So they're actually giving me the Q, not the P. Okay, they're giving me the Q. So the P is actually going to be 20%. The P is going to be those that are 6 feet or taller. Okay. But I guess before that even, what's the N going to be? Do you see what the N is going to be? The N is going to be the 35. You select someone, they're 6 feet or taller. Select another person, either they're 6 feet or taller or they're not. Select someone, they're 6 feet or taller or they're not. Select someone, they're 6 feet or taller or they're not. Oops. Okay, so N is equal to 35. Okay, and in this case, the success is that they're 6 feet or taller. Okay, so if you think of this as a random variable, right, you could let X equal number that are 6 feet or taller. That's what X is. Okay, because I want to find the probability that X is equal to 7, that 7 people are 6 feet or taller. Okay, so N equals 35. The Q is actually the 0.80. So they gave me Q, so the P is 1 minus 0.80, which is 0.20. Okay, so when you get a problem, they may give you P or Q. Okay, in this case, they gave me Q and I had to find P. In the one we did with the disease, they gave me P and I had to find Q. So I call this minding your P's and Q's, right? You got to mind your P's and Q's. You got to pay attention. What am I finding the probability of? That's my success. This percentage is are the percent of failures, so the success is 1 minus that. Okay, and then what I want to do is I want to find the probability that x is equal to 7. The probability that x is equal to 7. Okay, because I want to find 7 people catch the disease. Okay, so now 35 choose 7, so the total out of 35 trials choose 7 to be successes. That's how I think of that. The probability of a success raised to the number of successes I want, which is 7. The probability of a failure raised to the number of failures. So the number of failures would be 35 minus 7. So if I want 7 successes, I want 28 failures. In other words, these are going to add to 35, right? And then I can put this in. 35 choose 7 times 0.2 to the 7 times 0.8 to the 28th. And there I get the probability, 0.1665 if I round to 4 decimal places. That would be the probability that exactly 7 people are that are 6 feet or taller. Okay, so there you go. That's the binomial distribution and the binomial probability formula that you can use to find the probability of x successes. And so I think you need to get some practice with this now. So in the next video, I'm going to give you some problems to do.